And our speaker today is Chandra Sekar, and a big welcome to you, Chandra. His topic is oversized air conditioning systems and overcooled buildings in hot and humid climates. I won't give a full summary of his many achievements, but he's a highly expert speaker, and we're very, very delighted and privileged to have him. Just briefly to say, Professor Sekar will explore why air-conditioned buildings in hot and humid climates are often so cold that one gets reminded to bring a jacket when going to the office, the great irony of air conditioning in our age. He will consider the consequences of raising the set point temperatures as a means of improving the situation and expose some of the engineering challenges that necessitate a relook at the way air conditioning buildings in such climates are designed. So therefore, it gives me great pleasure to hand over to our CIBSE ASHRAE Group speaker for today, Chandra Sekar. Over to you, Chandra.
Thank you very much, Ewan, for those kind words of introduction. Well, the first I started to put this together as a talk, I was trying to figure out what exactly does the tropics entail. And I was surprised when I figured out that quite a few of us live in the tropics, more than 2.5 billion of us. And then if you look at it in the context of increasing effects due to climate change, it's only obvious that there's going to be more and more demand for air conditioning. Once we look at air conditioning demand, then the thermal comfort issues that go with it, which is the topic of what we're discussing this afternoon, is extremely important. So I just try to put this in the context of the number of people that this issue impacts. Three fundamental points, or three questions. Why are air-conditioned buildings in hot and humid climates so cold? Would raising the indoor set point temperature in overcooled buildings be a viable solution? What are the engineering solutions to this problem of overcooling in buildings? I start off with a typical air conditioning system that we have in the tropics, and I'm sure it's probably not very different to climates in London and elsewhere, at least for your summer air conditioning sort of design. We're talking about a room as an example here, but this could be a complete floor or the entire building if it's not too large a building. Then we've got an air handling unit that's going to push the air through a system of ductwork, and then we've got the return air coming back to the air handling unit. And what I would want to highlight here is in the tropical design, we recirculate a good 90% or thereabouts in terms of the return air back into the system. That's because this air, the return air, is still pretty cool, let's say, and we wouldn't want to throw away all that cool energy out into the atmosphere, into the outside environment. And not to forget that the outside air that we need for ventilation, the 10–15% sort of requirement, has to come from a very hot and humid condition. So there is a high energy penalty if we take high outside air percentages. So a 90% recirculation rate, or roughly about 10–15% ventilation requirements, is the common design. And then I would like to highlight here that the cooling coil, which does an important job in trying to address the sensible cooling load and the latent cooling load, is at the critical part of the entire design process. If the cooling coil doesn't do a good job, you either are going to have conditions that are not comfortable in terms of temperature and perhaps also in terms of humidity. So this is the basic design that we have for most buildings, in fact all air-conditioned buildings in the tropics. And the larger the building gets, the more complicated in terms of the design of the air handling units it becomes. And I would just like to state that let's look at this typical system, a typical air handling unit. And now if we start looking at the first question, why are these buildings in hot and humid climates so cold? I think it's fundamental to bear in mind here, as I just mentioned, the performance of cooling and dehumidifying coil, which really needs to be looked at very carefully. This has a very strong bearing on the indoor temperature and humidity conditions, which also consequently has a significant impact on the indoor air quality. One important consideration here is we first respond to the thermal conditions in an environment before we start to look at how it impacts in terms of the indoor air quality, more so in terms of how we perceive the indoor air quality. So the thermal comfort does become an important immediate response that all occupants have in any built environment. So if you look at this cooling and dehumidification requirements of the coil and how it provides environmental conditions in the space, the key design criteria, I would like to look at it in the context of two parameters. The first one is the room sensible heat ratio, which, as we would know as designers, is the total estimation of the cooling loads, which all of us are aware of consists of the sensible cooling load due to the conduction gain that comes from the opaque surfaces, the wall, the windows, the solar heat gain, the lights, the other equipment, heat, and so on and so forth. And then we have the latent load that primarily comes from the occupants. That's in terms of the room sensible heat ratio. Then when it comes to the cooling coil, as I showed you in the earlier schematic, we then take in a certain amount of ventilation air. So you got to add the system requirements in terms of the ventilation energy requirement, and you got a slightly different number in terms of the coil sensible heat factor. So you got two things. One is at the room level, the room sensible heat ratio. It's got a certain ratio in terms of sensible and latent load, and then you got a coil that needs to sort of handle or offset these loads. Now, all of us know from fundamental design considerations and the psychrometrics that we are taught from early engineering curriculum that the coil sensible heat factor or the coil performance must be compatible with the room sensible heat ratio. In other words, whatever is the nature of loads in the room that needs to be handled by the cooling coil. Let's look at it a little bit more closely in terms of how it happens in the entire system during its operation stage. Now, when we select a cooling coil, we would probably go to the whole process of finding out what's the total cooling load, how much of it is sensible and how much of it is latent, and then we could perhaps select a coil that is designed for a certain chill water flow rate, a certain temperature difference across the supply and the return of the cooling coil, and then you find that we trust that the system will respond well at other conditions. If the design condition is correct, and the problem is right at the early design condition, the very first point, the starting point, we notice in most situations that the condition is not quite right, simply because the nature of consulting practice is such that we tend to build in factors of safety along the way. So the issue of over-design without elaborating much on how it comes about is something that is not uncommon. So we would find that the coil that gets selected is already an over-designed cooling coil. The chill water flow rate is probably not the right value it should be for the actual condition that we want to experience or we will be experiencing when the building is being commissioned. So the issue of over-design is a very big challenge. So how does the system work in terms of the air handling unit operation? If you have a very large capacity due to an oversized coil, the only way you're going to change that capacity is by throttling the chill water flow rate. So we throttle the chill water flow rate, what we refer to as the modulation of the chill water, and this is where it gets very interesting. When we select a cooling coil for the sensible heat factor, and we say that this coil would work for a given cooling load, we would have matched the performance of the coil in terms of the sensible and the latent cooling to what we need in the space, in the building, in the room. Now, when we throttle the chill water flow, think about it. What's going to happen is the large cooling coil now receives less chill water flow, and it's going to make the surface temperature of that coil rather warm. The warmer the surface temperature, you have less dehumidification occurring on the coil surface. And that's exactly what I show on this slide. the nature of design, the way coils are selected, the way they are installed in the air handling unit, and the way we operate it, the coil tends to become too big, even at the starting point of the cooling coil operation. Let me continue to elaborate this through a psychrometric representation. Here it is. We have the space that we need to maintain at condition 4, maybe 24 degrees Celsius thereabouts. And this is the return air condition in the air handling unit. We mix with the outside air, which is hot and humid. And 2 is the entering condition of the cooling coil. And if it goes down to the off coil condition, which is 5, and this is the slope. 4 to 5 is the room sensible heat ratio line I was talking about. And in this particular slide, the slope of the coil is compatible, so everything is fine. If only we could replicate this at all times in the cooling coil operation in an air handling unit. Unfortunately, it doesn't happen. The coil is oversized. We try to maintain the off coil condition, say in a VAV system. I'm taking the example of a variable air volume system. We try to keep the off coil condition, say at this point 5, state point 5, because the chill water flow has been modulated or throttled. You tend to see that temperature is achieved, but the humidity is not. It tends to go a little higher because it, as I said, the 2 to this new color that you see here, the yellow color, is the new compatible slope of the coil, but then it is occurring at a different humidity level. So the consequence of that is the space is going to be slightly humid. If we say that we're going to get the right humidity, which means that we have to be the same dew point as the 5, then we tend to overcool it. But because we can't use active reheating in most designs, in Singapore we are not allowed to use active reheating for comfort air conditioning, we tend to leave that condition cold. The consequence is the humidity is right, perhaps, but the space is cold. So you got the choice. I mean, you got to pick what you want to have in terms of room condition. Something that's right in terms of temperature, but more humid, or it's correct in terms of humidity, but cold. So it's cold or humid. So this is the problem that we experience, and a lot of times we hear from facilities managers, people complain it's too hot, it's too humid, that they just tend to overcool it, and then, you know, we tend to live with this overcool condition. People wear jackets, they try to adapt themselves through extra clothing, but that's not quite what we want to have as a design and an operation of the system. Now, I'm going to pose this question here, the second question. Would raising the indoor set point temperature in overcooled buildings be a viable solution? We did a study in our campus probably about 10 years ago, and this slide is just highlighting to you the issues in terms of energy consumption, which is quite true, the high energy penalty I alluded to earlier. Rooms are maintained cold due to the point that I mentioned in terms of addressing the humidity. So there was a drive, in fact there is still a suggestion, a recommendation to aim for a warmer air temperature, space temperature. Now let me not say that I am not advocating that. I'm certainly advocating for a warmer temperature, a warmer space temperature, but space temperature alone is probably not going to be a very good idea. So let me just show what happened in our study. At 25 degrees Celsius is the elevated space temperature that I'm talking about, that we were kind of advised by our facilities office in our campus to try and maintain these conditions. And sure enough, it was done. And I had a student who went on to study 3 different offices, or 7 offices on our campus. I thought it was 3, he actually did 7. And used the usual ASHRAE 7-point scale for thermal sensation. We had about 146 respondents who participated. We measured the thermal comfort parameters, and he did measurements at several spots and 2 different windows of time, a morning time and an afternoon time. And of course, he did the usual PMV, PPD kind of computation. And let's look at the results, what came from that. We found that about 60% of people were comfortable in the usual way of trying to see how they perceive the environment. So there was a good percentage of people who felt that they were not quite comfortable, not all that comfortable as they used to be in the past. Remember, this was a building that used to be run at 23 degrees thereabouts, and then it was raised by a couple of degrees. Now, these were the measurements, and you can see from these temperature measurements that even in the morning time, before lunchtime, the temperatures were 24.5, 25, and higher. And in the afternoon, they in fact were even higher than 25. That's because the set point temperature was kept high, and it was not precisely being controlled to keep at 25 degrees. So these are the measurements that you can see. What I want you to take note of here is this fact that the air velocities were all very low, less than 0.1 meters per second. This is an important point which we were then able to relate to some of these other observations that we got here. What did we see? From the thermal comfort questionnaire survey in all these seven office spaces, we did two kinds of computation. One is the usual PMV, PPD computation, as I mentioned, and here you notice that in the morning and afternoon there were, well, 20% dissatisfaction, but later on it wasn't that bad. So you notice that the conventional or the typical PMV, PPD didn't show there was any serious issue there. But then if we did it slightly differently, just look at the comfortable response that we got, we noticed that the percentage of dissatisfaction actually was quite high. In fact, ranging from, say, 13% to even as high as 60%. That was the one I showed you as a general response in one of the offices earlier. So now if we try to look at it, there was this theoretical kind of deviation between the theoretical predictions, that is the PPD computed from PMV, and the actual dissatisfaction expressed by the respondents. We attributed this primarily due to poor air movement as the main reason for thermal discomfort. And in our observations here, we go on to say that temperature alone being raised may not achieve the optimal thermal comfort, especially with a system that was designed to be operated under totally different conditions, especially it was supposed to be operating under the lower temperature conditions. Humidity needs to be addressed, and the air movement part needs to be addressed. And this is where I would like to bring about what is now a recommended practice, and we certainly appreciate what can be done here. Elevated airspeeds at warmer temperatures certainly is a good way to go. When you increase the temperature with increased airspeeds, it certainly provides a better level of comfort. And we have done other studies in our environmental chambers in our department in the university, where we try to get tropically acclimatized subjects as part of our experimental protocol in the human response studies. And we have observed that 0.3 to 0.9 meters per second sort of phase of air velocities are found to be quite comfortable. People like it. It's no longer a perception of a draft, rather it's a perception of a pleasant state, increased air velocities. I just put this slide from the ASHRAE comfort zone, Standard 55 2013, showing the two different comfort zones. This is the winter zone and this is the summer comfort zone. And we would rather want to be in the green patch of this comfort zone. Invariably, we find that conventional buildings, the overcooled buildings, you're looking at the red comfort zone. Why would we want a very cold temperatures in the building when the outside is on the warmer side? So we should be aiming for the green comfort zone, and that's what we have been always reading in the literature, and that's what we teach in our curriculum as well. The elevated airspeeds, just a mention about how it can be useful and how ASHRAE provides this as a design guide. What you're seeing here is airspeed. I'm going to look at the meters per second, which is on the right-hand side, as a function of the temperature rise, which is on the top x-axis. And you notice here that when you have that radiant temperature equal to the air temperature, in fact, this is basically for each of TR minus TA, when that's 0, in other words, the radiant and the air temperature is the same, if you have an increased air temperature or increased temperature you want to work with in the occupied zone, increasing the air speed is certainly a way that can achieve that level of comfort. Again, we find that if the radiant temperature is greater than the air temperature, such an effect is much better perceived. People like it, and it certainly has a positive effect. If the radiant temperature is lower, in other words, the air temperature is greater, then we find that the effect of elevated airspeed is not all that significant. So when you have the radiant temperature greater than the air temperature, the elevated airspeed does have a much better positive effect. This is again one of the form of the same elevated airspeed comfort profile, where you notice that if you are looking at the operative temperature and the airspeed and the y-axis here, for predicted mean vote, which is less than, well, between 0.5, minus 0.5 and plus 0.5, you really don't need too much of an airspeed. So in fact, less than 0.2 meters per second. The light shaded portion that you see here, let's look at more of the summer comfort zone. You don't need local control of airspeed. This could be kind of a ceiling fan or a table fan kept in the middle of the room and serving a few occupants. It could still achieve even up to 0.8 meters per second. You are able to see a level of comfort. But when it goes to in this range, the larger or the higher elevated airspeed, then we are talking about local control, like a small fan in front of a person on the table, or what we talk about in the context of an air terminal device that ends on a person's workstation or work table that's providing an individual air supply. So these are local airspeed control, which is a dark shaded space, as compared to the lighter shaded space where you don't need local control. A general fan would serve the same effect. Now I want to go and talk to you a little bit about, so what's possible? We said increasing the air temperature is not going to work by itself. We need to relook at what's happening in terms of the other parameters. So what can we really do? Systems are oversized. So the question of a solution that we could be looking at in terms of overcooled buildings, what we really need to do, if only we could change that oversized coil during commissioning, perhaps replace that with a smaller coil, maybe we would have done the job. If only we would have sized the coil correctly, maybe it's not so bad. Even if we had sized the coil correctly at commissioning and installation and commissioning, when the loads change through the day, through the various months, and through the year, because it's bound to happen, cooling loads in the space are never constant, we will have several hours of part load operation. The coil is oversized for such a condition. So it is inevitable loads are going to be different. What we design and what we install, the nature of operation is such that we need to go through a peak load and a whole series of part load conditions. So one strategy I'm going to discuss with you now here is how we can work with this changing requirements of the coil size. The other one I'm going to discuss with you is about how we can optimize the coil parameters in terms of the delta T that we have through the coil, the fan speed, in other words, the volume of airflow, and so on and so forth. Let's look at the first aspect of it, an oversized coil in which we can have a dynamic change of the effective surface area in the operation stage. So this is being done through a simulation study. We look at a hypothetical building where I say that the actual maximum, actual peak cooling load is 100 kilowatts. The coil actually was selected to have a capacity of 200 kilowatts. So the oversized coil is 200 kilowatts. The actual coil I really need is only 100 kilowatts. The peak load is 100 kilowatts. Some basic parameters that you have listed here. Just a point I would like to make here that I'm going to make some of these information available to Tim and to be passed on to members later as handouts. So don't worry about some of the specifics and the details. You can pick it up later at leisure. So what I would like to highlight here is we looked at the condition that we have in the outside environment. We looked at typical conditions of what the space might be, the leaving coil condition that we want to design for. A typical chill water supply temperature of 6 degrees Celsius was adopted in this particular study. And here I have a table. First, I will discuss in the form of this table where an oversized coil is compared with a dynamically varying coil. So the base case is my oversized coil. The red numbers are the critical ones that I want you to probably glance your attention to. A 6.45 meters per second, meter cube per second airflow, 200 kilowatts capacity. And I'm going to use the sensible heat ratio that I get from a standard coil selection program as the basis to see how I'm doing in terms of the sensible and latent cooling coil performance. So I got a 6-row deep cooling coil. When I install it, I call this the series A1, where I notice that my actual load is only 100 kilowatts. There you go, 200 oversized, 100 is what I really need at commissioning. And when I try to use the same 6-row deep coil, I'm looking at a 62% sensible heat ratio. The smaller the number, the better it is for dehumidification. The higher number means that I am compromising on dehumidifying performance. Then I try to see if I can change that to a 4-row deep coil. Well, not that significant, not that big an important change. But when I change that to a 3-row deep coil, I do begin to see for the 100 kilowatts a significant drop. In fact, this becomes more obvious when I try to look at the part load conditions. Here I have the same 200 kilowatts oversized coil, the same large coil for the part load 50 kilowatts operation. Look at the very, very high sensible heat ratio. In other words, the humidity control is pretty poor. And then I change that to a 3-row deep coil. I can bring it down to about 75%. In other words, we're talking about a relative comparison. The smaller the coil, in other words, you customize the coil for the actual cooling load, you will get a better dehumidifying performance. So here I'm going to take you through, in terms of psychrometrics of it, the dark blue line is my oversized coil, 200 kilowatts. The red line is the one that I force my oversized coil to deliver as a 100 kilowatt performance, and the green is when I change that coil size to a smaller coil. Now what happens when I have a part load condition? The blue remains the same, which is my oversized coil. I don't see that load anyway. My actual load is 50 kilowatts now at a part load condition. It's very, very humid because you see you hardly get any dehumidification here. And then if I change that to a smaller coil, I come down to my yellow performance. So I'm going to show you a very simple movement of the space condition. If I have the red line performance, actual load 50 kilowatts, large coil, this is where my space is going to be. It's going to be at the yellow condition here, which is very humid. If I change the coil to a smaller coil, it comes down to the green. So basically my space condition goes up and down a vertical line, the space temperature set point, depending on how my coil can perform. So the lower I can bring that point on that temperature of 24 degrees, the better I am. So what I've just shared with you is changing the surface area of the coil, taking a smaller coil, I would get a better coil performance. How am I going to do that in practice? I have a large cooling coil selected, a design for 200 kilowatts. It's installed. What I'm going to do with that? This is where I would like to put forward something that was part of my own PhD several years back. We noticed that the driving force for condensation is the interface temperature. A low heat transfer coefficient on the air side, which means a low phase velocity, accompanied with a high heat transfer coefficient on the water side, which means a high coolant velocity, is the way to go. Low phase velocity, high coolant velocity gives us that lowest or the coldest interface temperature. So I'm going to show you schematically how we can achieve this in practice, not just at the peak design load, but during the part load operating stages as well. Here you see a 6-row deep coil, the same one that I discussed with you in the table earlier. We got the counterflow arrangement, airflow from the bottom to the top of the screen, and the chill water supply to the supply manifold going to rows 6, 5, and 4. And just a little change that I'm going to do here, I collect the water after row 4 into a return manifold, and then I got a little bit of a manipulation of the flow of the chill water. I feed it back into row 3 through another supply manifold, 3, 2, and 1, collect it in this, collected in this manifold, and we have the modulating valve here. See, everything is the same as you would see in a typical conventional design, supply and return, but with this modification here. What's going to happen is if I have my design load as I actually designed for, this should work. And I'm doing exactly what a typical consultant's design would be. Now at part load, the problem is the coil is oversized. What I can do is, how do I make this large coil become smaller? And this is where my manipulation of the chill water circuiting allows me to do exactly that. Notice what's happening. I have effectively rendered row 1, 2, and 3 inactive. I supply to row 6, pull out the water from row 4, so only 3 rows of a 6-row deep cooling coil is functioning at this stage, which is what I discussed with you in the table as well. A 6-row down to a 3-row at part load, we notice that you'll get a much lower sensible heat ratio of the cooling coil. So this is a strategy, and then it's very simple. We got a 3-way kind of bypass valve here. Earlier, I made sure that this particular valve was closed. The water could be circuited this way, and then in this particular configuration, I closed this valve. So basically, only 3 rows are going to be used. What's happening here is these 3 rows still exist there. They are just dead component of chill water tubes in the circuit. It's not contributing to any performance, but that's okay. I'm now effectively working with a smaller cooling coil. When you have a smaller cooling coil, the modulating valve that was closing in the earlier 6-row configuration, I can open it up and bring it back to what my design flow rate was. Remember the high coolant velocity I mentioned as a part of a requirement? I combine the low phase velocity together with the high coolant velocity at part load, and I get the best dehumidifying performance. So the key finding from this particular study was the practical challenge to an oversized coil can be mitigated by making sure that we work with an effective surface area reduction through the operation stage of the coil. 6 rows to 3 rows, and I just showed you one example. We could be looking at a 6-row to a 4 rows to a 3 rows, and that's kind of a design detailing one can do right up front to make sure that we are able to get a better performance throughout the operating stage of the cooling coil. The second strategy I would like to discuss here, well, it's not quite a specific technology-related strategy, it's a concept. From a design consideration and concept, how do you want to go about it? The issues that I'm trying to address here are space temperature difference, cooling coil and fan energy, and related IAQ issues. So here, from the point of view of ventilation, IAQ, and energy, the coil performance, no doubt we've seen the relevance and the importance of it, the fan energy, and the space delta T. Now, the space delta T is the temperature difference between the room condition, say like 24 degrees Celsius, and the supply air temperature. It's not the off-coil condition, but the supply air temperature. That's the space delta T we're talking about. So now, if you look at the psychrometric chart here, it's kind of a busy chart, but basically the different conditions I'm looking at, there's a base case, a conventional 8-degree delta T, I'm looking at it, which is a condition D in the entering point of the cooling coil, and then I go down to these other 3 points, A, B, and C. So C is 7-degree delta T, it's a reduced delta T, 6-degree, and 5-degree. It's quite obvious, all else being the same for the same cooling load, when you reduce the delta T, the airflow increases. So it's as simple as that. So what is the implication? What the point I would like to highlight here, at all these various possible operating conditions, space delta T of 5 or 6 or 7 or 8, you got to make sure that they end up on the same red line. That's the load ratio line of the room sensible heat ratio. That hasn't changed. Remember, we said that's an important design criteria. The further away you move from the saturation line to be on this line, the more challenging it becomes to achieve that condition. The simple reason being, for a cooling coil to come to a space delta T, say like this condition here, what I'm showing you as a space delta T of 5 condition, it's got to overcool and dehumidify and then reheat itself to get to the right condition. So the further away you are from the saturation line, the more challenging it is and the more energy penalty you would incur. Again, I'm not even bothering to look at this slide in any detail. All I would like to highlight, when you see this later in the handout, you can look at the specifics of it. I got the base case, the 3 cases here, and also another situation where I'm increasing the ventilation kind of requirements. What's the consequence of it? When we look at the implication, 8 degrees delta T, that's my base. I started that as the base case. I have a certain level of energy consumption, let's say, and my energy, well, of course, that's my base case, so there's no difference, no additional energy required. If I change that to a 7 degree delta T, it's going to get worse because, as I said, smaller the delta T means my off-coil condition and thereby the space, the supply air condition is getting warmer. The warmer it is, the more energy it's going to be consuming. The reason for that is there is an extra cooling to be done, the overcooling part, to address the humidity issue, and then the additional reheat consumption that we need to provide for. And notice the other consequence. The smaller the delta T, we also increase the fan power because you now need to move a lot more air. So again, from an optimization kind of a consideration for the cooling coil, if we work with a larger delta T, space delta T, it's always a good idea. Sometimes we encounter situations, consulting practice kind of discussion, we find that there's a tendency to have a warmer supply air temperature. The problem is humidity needs to be handled, and in doing so, it could actually incur a higher energy penalty. This is just another way of looking at the same issues. Space delta T, well, you got the different cases, 8 degrees Celsius, 7 degrees Celsius, 6 and 5 degrees, and here are all the energy consumption increase that we're talking about. And you can see here, the total energy consumption can be quite drastically increased if we move away from, say, a base case of 8 degrees to a lower delta T of 5 degrees Celsius. As I said, as one last kind of a consideration in that particular study, we looked at what happens if we were to increase the outside air percentage. So, of course, increasing outside air means there's more energy requirement. Now, this could be necessary in some cases if we are talking about the increased occupant density and you need to account for more ventilation. We find that as you increase the ventilation, the energy consumption increases. So if, let's say, you kind of have a 10% increase in the ventilation or 8% increase in ventilation, that would translate to about 18% increase in the energy requirements, the additional capacity to be installed there. So what were the key findings from this particular study? The total power requirements, which comprises overcooling, reheating, and increased fan power, increased quite significantly as the space delta T decreases from 8 to 5 degrees Celsius. So the key point here is, let's try to have space delta T that are larger rather than being smaller. The total power for a design involving a space delta T of 5 degrees Celsius can be as high as a factor of 2.2 of the total power requirement for a space delta T of 8 degrees Celsius. And of course, the implication of higher supply airflow requirements on the duct size and the associated fan power requirements, additional fan power requirements, problems that will go with it. And so what becomes an important outcome from here is that we need to look at the optimized coil configuration and its performance to ensure that we address the issue of both the indoor air quality and the thermal comfort and the energy aspects of it. So I would like to conclude by going back to those same three questions. Why are air-conditioned buildings in hot and humid climates so cold? What I mentioned earlier and discussed with you is due to the oversized design of air handling unit, particularly the cooling coil, and an oversized coil will tend to have less dehumidification unless we employ overcooling. And this situation worsens when we are looking at part loads. Would raising the indoor set point temperature in overcooled buildings be a viable solution? Well, the answer is no. Raising the set point temperature alone is not a solution because we have issues related to dehumidification, which is basically the question one that I highlighted just now. The problem is still essentially one of handling the latent loads, the dehumidification requirements from a large coil. What are the solutions that we can resort to? Well, we can look at a dynamically varying surface area of the cooling coil, which would allow us to literally customize the coil size, the effective surface area of the coil, to what the cooling loads might be in the building, in the space, as it goes through its dynamic range of operation. We have done other studies, which is not part of what I'm going to be talking about in this talk anyway. Then we said, why don't we look at decoupling the ventilation requirements from cooling? That is yet another talk that I have, and some work that we've done in our group, where we separate the ventilation requirements, handle the high humidity loads through a separate heat mass transfer process, and then we provide the sensible cooling through another different track. And that combination also provides tremendous advantages, both in terms of individual zone level ventilation control, demand ventilation control, and provides a much better overall performance. So with that, I would like to thank you for your attention and pass the screen back to is that Tim or even at your end, and I'll be happy to take questions. I don't know how you want to go with this process. Thank you so much.
Okay, Chandra, thank you very much. That was extremely interesting and some tremendous work gone into that presentation. So thank you. I'd just like to point out to everybody that we've had the privilege of listening to Chandra, who's a professor at the School of Design and Environment at the National University of Singapore, and a distinguished ASHRAE lecturer. I've been looking through some of your honors. I won't read them all out. I'll save your blushes. But as well as being a distinguished ASHRAE lecturer for almost 10 years now, Chandra also received the ASHRAE Exceptional Service Award in 2013. So we're very privileged to have you, Chandra, speaking to us. We have had quite a lot of questions coming in, so I'm going to try and manage that process now. We haven't got a lot of time, but we'll canter through them quickly. We had about 80 people online with us today, so welcome to you all around the world. A quick comment from me, very interesting this year in the UK, and I think in the US as well, they've been looking at gender issues related to overcooling of offices. Women tend to feel the cold more than men, and there was a feeling that that wasn't being taken into account by many of the set points, the set point temperatures in commercial offices. Made quite a stir in the UK this year, but I think that's a subject for a whole other presentation. So the gender impact on air conditioning. So one for you to consider, Chandra. That's okay. Yep. We won't get into that. That would take too long. Okay, so I'm going to try and get through some of these questions. Thank you to all of you who put them in, and I apologize in advance if we don't get through them all. We will maybe try and address them offline with Chandra separately. But Chris Sheck came in immediately. You started, Chandra, and Chris is in Brooklyn, New York. So hello to New York. His question was, is the threat of global warming a justification for oversizing? Is that something you could address, Chandra?
Well, let me respond to that question by saying that we probably would not want to have an oversized system, not just of the coil or any other part of the system and plant of air conditioning in a building. But it is inevitable that some sort of a buffer or capacity buffer would be provided in any design. So for several years, I've been trying to engage in discussion with consultants to try and see why can't we just do the correct cooling load estimation and go ahead with that. I think the issue is one of, I suppose, capacity being adequate and not to be found lacking in capacity requirements. So my response is, well, we probably cannot run away from an oversized, well, I won't say an oversized system, but some kind of an additional capacity system. But the main challenge with cooling coil is any increased capacity or any oversize that we build into the system goes against the basic consideration of the correct surface area requirement for the latent cooling load handling. In other words, we need to work with the fact that you're going to have an oversized coil. How can we then make it adaptable when we have varying cooling loads? So even if you have a peak design that is correctly designed and estimated, when it gets into a part load stage, we do have that mismatch between what the coil was selected for and what the actual cooling load is in terms of the part load. So my response is providing that flexibility in the design of the cooling coil and an air handling unit is probably a good idea, and that's what I'm trying to advocate here as a design concept, which will have to be translated through manufactured cooling coils that can get into place. So the consultant, if he says that, well, you are reducing my coil size, I said that's not a problem, because if you actually had your peak cooling load, my coil is no different from your coil.
Okay, thank you. That's a good. That's a very good response. Thanks, Chandra. We also heard from someone who described themselves as Spyridon. So I'm not sure if that's a company or a person. Anyway, I guess you know who you are. Interesting question. Does it make a difference to indoor air quality what cooling medium is used? For example, chilled water or refrigerant. Does one behave better to changing outdoor conditions, or is this just simply down to the overall system design? So a question about the cooling medium, Chandra.
Okay, I think fundamentally, from a conceptual point of view, what cooling medium is used is probably not going to be that critical, but let's translate that in terms of how systems are actually used in building designs and are available in the market. You see, when we have refrigerant-based systems in smaller applications, that is, a split system units or otherwise, the issue of indoor unit versus your heat rejection unit being outside, it is a great system where you move the noisy part and the heat rejection part to an outdoor environment and just have a fan coil move around within the room. The only issue is we don't provide for any ventilation. So that becomes a critical question, and I think I have another topic that another topic where I discuss this at length. So conceptually, how we cool the air through refrigerant or chill water, I don't think there's a big difference. But at the system level, if we don't adequately provide for ventilation, which tends to be the case with the refrigerant-based systems, then it will potentially lead to some questions or concerns about indoor air quality.
Okay, thank you, and my apologies to Spyridon. It's been pointed out to me that Spyridon is in Greece, and that's a Greek name. So apologies, not a company, a person. So thank you, and I hope Spyridon that answers your question. Christopher asked, well, it was more of a comment, or he was making a comment and wondered what your reaction was, Chandra. Undersized coils contribute to chiller low delta T problems, and that reduces the chiller capacity. Thoughts on that?
Well, that's where I think a kind of a match or a balance between the actual load, expected loads on the air side, which are, i.e. the cooling coil capacity, to what the chiller loads must be. So I think I fully agree with that point. An undersized coil, I don't think we want to undersize the coil. Rather, we want to translate that same level of flexibility we build into the cooling coil operation back up the chain into the chiller sequencing or chiller operation. So yes, I mean, that's why these challenges have kept us all in business, I guess, over the years. It is not easy. I mean, I fully appreciate the point.
No, fair enough. It's yeah. Well, we need to keep busy, don't we? I need to keep coming across these things. So, thank you. Renier asked, does a higher supply air temperature and lower delta T not improve the coefficient of performance and offset the reheat and fan power increases. Is that something you can address?
Well, the higher, well, I'm not sure if I am with you on that reasoning, because when I say the higher supply air temperature, to get to the supply air temperature, you would probably have to do an overcooling part. Otherwise, you can't get the right humidity level. And that was the point I was trying to make earlier. It's very difficult. I mean, I am talking about a conventional vapor compression-based system. If you're going to achieve your latent load through some other means, desiccant system, it's a different computation. I didn't do that. I'm just taking the case that you got chill water supply, temperature coming at 6 degrees. I think I used 6 degrees in my simulation, and I'm trying to ensure that we stay on that red line, the load ratio line, because that's the nature of the cooling loads in the space. I'm not changing the space temperature, mind you, I'm changing the supply air temperature. So to get to that right humidity level, we will still probably have to use the overcooling and reheating concept. Okay.
All right, thank you. Yeah, I can't give much more detail on that because I'm not technical enough. So thank you for that. I guess we're running out of time. Tim, can I just check with you? It's now 1 o'clock. Do we have to wrap it up, or can we? I've got 2 more questions here.
Okay. Well, we've actually got a whole raft of questions still coming in.
Yes.
We could be speaking probably for another hour with questions that are coming in now. They're whizzing in. I guess we can roll on for 5 minutes if Chandra's okay to hang on for another 5 minutes.
Go ahead. I'm fine. Thank you. No problem.
Okay.
Okay. Well, why don't we? Okay. Sorry, Tim. Why don't we? I posed the 2 questions that we had. I've seen there's 2 or 3 just suddenly come in at the last minute, and perhaps we could address those at a later date or send them on to Chandra and do something via the website. Would that be possible?
Sure. I think we can work that. Yeah.
Okay. All right. Well, there was a question from Robert. Did you assess what the payback was on cost versus energy savings for your LFV and HCV concept? Did you assess the payback?
Well, I did not do a specific payback on the coil modification that I discussed with you, but I have discussed in terms of what is the implication for this coil. You see, the adaptable, I call this the adaptable coil. Basically, it's no different from a 6-row deep coil that you would probably get of a coil manufacturer wherever that's going to be made. And a modification of the nature that we're talking about here is just changing the concept or the notion of a standard 6-row deep coil of a certain fin per inch and tube diameter and so on. We change that to a kind of a, let's say, you got a whole series of the 6-row deep coil, but then a 6-row to a 4-row to a 3-row. So imagine that you change this whole thinking in terms of the coil supply to an air handling unit manufacturer, where he now knows that instead of just one 6-row deep coil, I can get this kind of adaptable coil. Personally, is the same amount of copper tubes and aluminum fins, perhaps a little bit of change in the way the cooling coil tubes and the jigs are going to be made. So I see it as very minimal impact in terms of the cost on the coil, but the benefit that you would get in terms of how you customize it in its operation is far going to outweigh the increase. I mean, anything that you change from a conventional manufacturing, instead of a 6-row coil being made in mass production to a modified adaptable coil, it's still 6 rows, but done slightly differently. Once that becomes the norm, I think the cost differential is going to be quite minimal. But I do agree it would need to go through that kind of a market acceptability from the cost point of view. From discussions within our group and talking to some consultants within here, our facilities side, they are very, very excited. I'm just waiting to see the first opportunity where I can try this on a reasonably decent scale in terms of the size.
Okay, Chandra, thank you. We've got Osman has asked quite a direct thing. He's suggesting you are making two contradicting recommendations. He's saying at the beginning you were asking us to increase air velocity, therefore hence airflows, but at the end increased airflows were increasing the energy penalty because of the lower delta T's. What do you say to that?
Well, what I'm trying to say here is the increased air speed doesn't have to come from your conditioned air. So basically what I'm saying here is you can have your temperature that you're providing from the air. You know, I mean, I don't think I was discussing a warmer space condition, warmer space temperature. So the point I was trying to make there with elevated airspeed, I mean, that's the way we would want to go. We would not want to use the AHU fan to provide that increased airspeed. We'll probably want to leave it to an individual control through a low energy involved fan. In fact, that's another kind of an area of work that I worked with some other colleagues where we are trying to work with what we call low watts fan, very, very small fans that doesn't consume much energy at all, and it's going to be used only when it's needed. You see, when we provide that individual control with the local control that I was talking to you about, different people use it differently, and there'll be some people who may not want to use it. So I'm not for one moment advocating that the increased airspeed be provided through the central system. That would not be a very energy efficient way of doing things. So I am not sure if I'm contradicting myself in that sense. Elevated airspeed locally for thermal comfort with warm temperature is a strategy to provide comfort. But if we look at what's going to come from the air conditioning system design and the supply duct, in other words, the AHU-driven fan, I would not want that to be a very high velocity in the space.